Welcome you to this series of lectures on marine hydrodynamics. In the last couple of classes, we have spent a good amount of time on understanding various aspects of wave motion in a fluid, particularly in water. And to be specific, in the last class, we have worked out few examples to understand the wave propagation in specific cases. We will continue that in today's lecture, so that our understanding on the wave motion will be very clear. As I have told in one of the lectures, that when you look at waves in the ocean, we come across waves whose period can be few seconds, and it can be few hours, it can be in number of hours. And like when you look at waves, like in case of a capillary gravity waves, it is in few seconds, whereas wind waves and other waves which are generally day to day affairs, then it comes around 10 to 15 seconds or 20 seconds. There are waves like tsunami, storms, where the wave period can go in minutes or in hours. When you go to tides, the wave period again goes more than it can be in hours, whereas the planetary waves are in number of days. The details one can easily get it from various textbook of waterways, particularly the book by C.C. May on the applied dynamics of ocean surface waves. Lot of information can be obtained from this applied dynamics of ocean surface waves. By C.C. May. Even it is a one scientific publication. World Scientific, this is published as well. So, today what we will do, let us work out a couple of more examples for a better understanding about the wave propagation problem. So, let us look at a waves in a tsunami. I am looking at a waves in a tsunami. It has a period, the wave has a period of 20 minutes and height period, that is t. The wave height is h, it is 0.6 meter. At a point in the ocean where the water depth is h is 3800. So, initially this was the data given. Now, this wave, determine the celerity of wave. Determine the wave celerity. Of this wave. Further, so wave celerity will be c is equal to root g h. If I assume shallow water, assume this wave is in shallow water. If I assume that, then what will happen? C will be root g h, and that is 9.81 into h is 3800. In fact, 3800, this is almost the average ocean depth, and that will give me 193 meter per second. So, that is the speed at which the wave will propagating at the depth of water if a tsunami type of wave. Now, if you put in kilometer, it is perhaps it will be approximately 695 kilometer per hour. So, it can be considered at the speed of an aircraft. Now, what is the corresponding lambda? Lambda is C t, because I am considering, and once lambda is C t, that is C is 193 into 20 into 60, because 20 minutes 60 seconds. So, that is the meter, and that becomes 231,000 meter, 700. So look at this, 231 kilometer, quite large. If you look at h by lambda, h by lambda will be h is 3800 divided by lambda is 231,700, and this becomes 0.016, which is less than 1 by 20. Thus, the justification of shallow water is justified. Our assumption is justified. So, the assumption of shallow water is justified. Now, with this understanding, now suppose what will happen to this wave. Now, I will go to the second part of the question. Second part is determine the wave celerity, length, basically I mean wavelength, and height in a nearest region nearest depth of 10 meter, assuming no refraction and diffraction. That means, if there is no distance, same wave is propagating to the shoreline, then what will happen to the wave celerity, wavelength, and the wave height in the nearest depth at the water depth. So, that means in the nearby region h is 10 meter. If h is 10 meter, then what will happen? Because again, if I look at the c root gh, g is 9.8 into 10 meter per second, and that will give us 9.9 meter per second. So, that is the speed where in the nearest region. On the other hand, in the beginning c was 193 meter at c 3800. We have seen that this was 193 meter per second. meter per second, whereas now near the when the water depth, so that means near the shoreline, the depth speed has decreased, the wave propagation speed has significantly reduced. Then what happened? What is my, if I apply energy conservation law, h square h root h 10 is h square root h to the power to 3800. This is comes from the law of conservation of energy flux that I have repeatedly using. So, I am not. So, basically it is coming from the equation that ECG is equal to constant. In case of shallow water, this becomes this. And then if I, what will happen to my S10? This will happen to 0.6 into 3800 by 10 to the power 1 by 4, and that becomes 2.645 meter. So, very interesting to observe, the speed of propagation is reduced, but whereas the water depth has gone to 2.645, whereas the initial water depth at h is equal to when it was at 3800, the water depth was 0.6 meter. So, that is what is more interesting to observe, the water depth has increased nearly by 2 meter. And if you look at lambda at this depth, lambda is Ct, and that is 9.9 into T is 20 into 60 meter, and that gives me 11 11 kilometer 900 meter. This is my lambda. So, this is what the wavelength. So, what we have seen that initially the wavelength when lambda was 3800, there the wavelength was 230, it was 231 kilometers, whereas this was this. On the other hand, here it has become lambda 10 has become this. So, the wavelength has significantly reduced, speed also significantly reduced, the water depth has increased, and that is what. So, this is one very interesting example to understand the wave propagation when the wave propagate from the deep water to shallow water, particularly in case of a tsunami. And all depends on the, it is becoming so large, the quantity is becoming large because it is because of the wave period of 20 minutes. Now, I will go to another example, that is also another interesting. This example will give us about, let us look at the basin oscillation. In the last class we have talked about that the time period associated with a rectangular basin oscillation is 2 by root g, closed basin I mean here 2 by root g h, if it is in shallow water depth 1 by m square by a square plus n square by b square. This is my period of oscillation. Now, what will happen if, this is another example, a closed basin, consider closed basin, this is the time period. Now, if I consider my basin is of length 30 kilometer, it is a lake of 30 kilometer length, B is width is 2 kilometer and the water depth of the lake is 100 meter. This is the data given of a particular lake or a lake. Then suppose the relaxation of wind set up a wind set up the mode m is equal to 1, n is equal to 0. Basically, there was a wind and then it has created the harbor, the lake starts oscillating and it set up the mode m is equal to 1, n is equal to 0. Then what will happen in this case? T10 2 by root g h, g is 9.8, h is 100, into 30 kilometer m, a by m, m is 1, n is 0. So, this is a is 30, 0, 0, 0, and this gives me, and that gives me, sorry, it is second, and that gives me how much? This will give me exactly 31.7 minute. So, look at this. So, this is the period of oscillation of the harbor, thus that is your T10. In fact, this kind of oscillation, as we have seen that this kind of oscillation in a lake makes bringing a lot of damage to the infrastructure that is available in the lake, whether it is the seawall, whether it is some of the existing facilities, it is always destroyed. 31.7 minute the harbor will go, the lake will go on oscillating, and that will generate a wave which will significantly create lot of damage to the. So, this becomes the period of oscillation. So, So, these two examples give us how the wave propagates in case of a tsunami and in case of a harbor oscillation or particular oscillation of a lake. And here look at the length of the lake, it is a very large lake, 30 kilometer length and 2 kilometer width, very large area, but it creates a wave of this period. So, these two examples that gives us a very good understanding about the wave period and the wavelength associated with the wave period of oscillation of a basin, particularly of a lake, and in the previous example it gives us about the idea how the wavelength and the speed of a wave that changes when a tsunami propagates. With these two simple examples, now I will go to another class of problem. Basically what happen, we always say that when h by lambda, we always talk about this is called the relative depth. This is a relative water depth, and when h by lambda is greater than half, we say it is a case of a deep water wave, and when you say h by lambda is less than 1 by 20, we say it is the case of shallow water. On the other hand, when 1 by 2 is less than h by lambda is less than 1 by 20, we say it is the case of intermediate water depth, waves in intermediate depth. So, that is about h by lambda. What will happen to capital H by lambda? How does this affect the motion of propagation of the wave? So, when it comes to this, in fact, sometimes this h by lambda, because wave height increases, we have seen in the previous example, one of the example in case of tsunami, that the wave height increases when the wave approaches towards the shoreline. H increases as the depth decreases. The question comes, can it, when h is tending to 0, whether h will tend to infinity? That is my question, but it really never happened this situation. So, what happened to the wave when wave propagate from the deep water to the shallow water region? So, there must be a phenomenon occurs that is called wave breaking, and this wave breaking criteria, it was developed in 1944. It developed a wave breaking criteria, and which all depends on the h by lambda ratio, that is called the wave stiffness. The stiffness of the wave increases this factor is called wave stiffness. In fact, Mitchell suggested after a lot of model tests that this h by lambda ratio gave a limit for this, and that limit in case of deep water is, that is h by lambda maximum value will be 1 by 7 tan hyperbolic h, and that is the criteria of wave breaking, Mitchell's criteria. And you can see that in case of deep water, we have kh is much 1, and in that case tan hyperbolic h. So, h by lambda maximum it can obtain 1 by 7. On the other hand, in the shallow water region, On the other hand, in case of shallow water, where kh is much less than 1, then we have h by lambda maximum value will be obtained is 1 by 7 into kh, and that kh is nothing but 2 pi by lambda, 1 by 7 into kh 2 pi by lambda, into h. So, this is what which gives, which can be written as h by h, because lambda is here, so this is same lambda. So, which gives h by h maximum is equal to 0.9. So, this is also particularly in case of shallow water, this becomes the limit, and in case of deep water, this becomes the limit. This is in case of any water depth. So, this is the criteria for, these are the criteria for wave breaking. So, in fact, this wave breaking criteria, there are 3 different factors on which the wave breaking criteria will depend. So, there are, I will not to go in this lecture to that details, but particularly when a wave, how they break, particularly when the wave propagate towards from the deep ocean to the shallow ocean, what happen? And if I say that this is my water depth, then what will happen? The wave propagates, sometimes they propagate break like this, and this kind of breakers are called, sometimes called the spilling breaker. Sometimes sometimes the wave they break like this, and this is called a collapsing breaker, plunging breaker, there is something called the wavelength. Some of the wavelengths, when the waves propagate, this is called collapsing breaker. Nice pictures will be available in textbook. And then there is something called surging breaker. I am not clear. So, these are the 3 major types of wave breakers, and better examples can be found in the book, some elements of ocean engineering. Any handbook of ocean engineering or coastal engineering, this can be detailed. Nice pictures can be, one can easily get it, various handbooks of various types of breaking, and all these breaking criteria depend on the slope. They depend on the slope. And there is something called sharp similarity parameter. In fact, when the wave propagate to the shoreline, friction also takes place at the bottom, and because of the friction along with the change in the depth, and these are certain kind of a slopey bed, but sometimes there is abrupt changes in the water depth. So, there also waves can break, because, and there are other phenomena will associated with this, that is the phenomena like refraction, reflection, those phenomena will associated with when there is sudden changes in the water depth, that will. Now, with this understanding about wave breaking, I will just work out another example. What will happen to the waves when the wave interact with the current? wave interactions current. There are various. I started with the very simple examples, but slowly we want to understand much more. Although that everything cannot be covered in this course, but I just try to introduce to some of the basic things which occurs in day to day affair, and a little understanding will help in later understanding in detail about the wave phenomena or the ocean, various aspect of the related to various aspect related to the ocean waves or related to the marine environment. But this will give us a very fundamental understanding about various things that is associated with the ocean wave. Suppose I have a current. When I say currents, basically currents are steady generated smooth movement. They are kind of a smooth movement of the water. Water which follow a straight or rectangular path or circular path. So, I will consider here today in today's discussion we will consider of uniform current. Let me consider, I consider this H. Current is flowing in the x axis. Let the speed be u, speed of current. And basically this is uniform speed. So, what will happen when there is a current? What will happen to the corresponding wave? So, are we still in the potential because it is a uniform speed? So, if I say that I have a invested fluid, then in the presence of current my velocity potential will exist. So, phi will be phi plus u x, because I am talking of uniform current along x axis. This is along x axis. So, phi can be, this is the speed of current. So, my new velocity potential will be phi plus u x. Now, then this is also the vector field is also, velocity field is also rotational. If since I consider the water as a rotational, so in the presence of a uniform current, rotational vector field, if it is a rotational vector field, then this also will satisfy automatically, this will also satisfy del square phi is equal to 0. And again we all know that in the presence of current, how the initially I know that when we have the free surface, we have bottom condition phi y, this phi will also satisfy this, and then we have phi y, this is also 0 and y is equal to minus h. This is satisfied in the fluid domain, whereas phi y is 0 and y is equal to minus h, that is basically on the bottom, and the free there is a wave profile, there is a wave with current, and here y is equal to minus h. So, here this will be satisfied. Now, what will happen on the free surface? The free surface will have two conditions, like we had the dynamic and the kinematic condition on the free surface. So, in the presence of current also the same condition will be satisfied with certain modification, and we can see the two free surface conditions will be in the presence of current, it will be del phi by del y is equal to del eta by del t. Eta is the free surface elevation plus u del eta by del x. And that will give us, and this comes from the same condition, because we have d by dt y minus eta, this is on y is equal to 0. This is the linearized kinematic condition, because this comes from here y minus eta is 0, and you have this is nothing but del by del t plus u del by del x plus v will not be there, because Okay, take it V del y into y minus eta. Here what is happening? I am putting phi is equal to phi plus ux. I put, so this will be minus del eta by del t. This side will be del eta by del t, and then if I take with this, then you have u is horizontal velocity, and that is nothing but is equal to phi x plus u. The horizontal velocity in the presence of current is u is the speed of current and phi is the fluid motion, that comes the horizontal velocity of the fluid particles plus speed of current into phi x plus u into eta, and then plus v del by del y, so plus v. So this is del eta, this is plus, and this becomes phi y. V is phi y, so that becomes del by phi x eta. That term will go because of we are looking at small amplitude waves. So we have del eta by del t plus phi x u del eta by del x, del eta by del x. So plus u del eta by del x, this becomes is equal to phi y. This is capital phi. So this is becomes the kinematic condition. This becomes on y is equal to 0. This is the linearized kinematic condition. If you look at the dynamic condition, what will happen? The dynamic condition will be, because we have phi t plus g eta plus half phi x plus u square plus phi y square equal to 0, basically minus p atmosphere, and this is minus p by rho at y is equal to eta, and this if you simplify on y is equal to 0, then you get phi t, plus g eta. From this, after linearization, you will get plus u phi x, and that is equal to 0. That is 0 on y is equal to 0. That becomes the, so, or we can write it in a simpler form, del by del t plus u del by del x into phi is equal to plus g eta is equal to 0. This is on y is equal to 0, and in fact this is the kinematic condition. In the presence of current, this becomes the dynamic condition. When we have a wave with current. So here if we put u is equal to 0, then you got del phi by del t plus g eta is 0, that is the dynamic linear dynamic condition, and here you get del eta by del t is equal to phi y, that is the. Now if you, what we will do here, I will just little simplification. Suppose I operate both sides by del of the dynamic condition, or I will take del by del t plus u del by del x. This operator I apply on the dynamic condition. If I apply on the dynamic condition, then I have already del by del t plus u del by del x, and that is phi. This becomes plus g del by del eta del t plus u del by del x. This is one of the interesting result into eta. This is 0, this is on y is equal to 0, but we know del by del t plus u del by del x eta is equal to phi y. So this becomes phi y. So that gives me, So, this will give me del by del t plus u del by del x square phi equal to g plus g del phi by del y equal to 0 and y is equal to 0. In fact, this becomes the free surface boundary condition in the presence of uniform current in one dimension. And then if I start with a simple wave, suppose I start with theta is equal to a cos k x minus omega t, then I can easily see I can get a phi which is of the form a cos hyperbolic k is plus y by cos hyperbolic k h sin k x minus omega t, and from this if I substitute for this, if I have a single wave profile of this, then phi will be this. It can be easily seen that omega minus k u square will give me g k tan hyperbolic k h. And that will give me the dispersion relation. In the presence of current. So, if I simplify further this relation, because that is so in the presence of a current there is a shift of the frequency omega by k u times, and in fact and that if I will go for simple two cases, that when k h is large, that means omega minus k u square is g k. On the other hand, when k h is much small, then we have omega minus k u square g h into g k into k h. So, that if I just bring k square this side, so this will give me omega by k minus u square is g h, which implies omega by k is my c minus u equal to root g h. And this can be plus or minus because this is a square part, and that will give me c is equal to u plus minus root g h. And this is one of the very interesting result. Particularly what will happen to c? What is c? C is the speed of propagation at which the wave is propagating. When u is equal to, if I take minus sign, so the positive sign means here two things. The positive sign is when there is a positive sign, that wave and current collinear currents. When wave and current are in the same wave and current in the same direction, wave and current in the same direction, then when wave and current are in the same direction, then c will be u plus root g h. That means the speed of wave propagation will increase in the presence of current. On the other hand, when they are in the opposite wave current in the opposite direction, if they move in the opposite direction, that means then there is a retardation in the speed of the wave propagation. And again, if we will see there, that means in that case your c is u minus g h, and if u minus g h is greater than 0, u minus g h is greater than 0, that means c is greater than 0. So, that in that case the wave propagate in the positive direction, in the forward direction. On the other hand, if c is less than 0, that means u is less than g h, root g h. If this is this, then you have c is less than 0, and when c is less than 0, the wave propagate in the opposite direction. Backward direction. So, that means, and again there is a situation here we have when u is root g h, which implies c is 0, and this situation gives no wave condition. And same analysis we can think of the same analysis in case of deep water and also in any water depth, intermediate depth. So, in fact, this was a G.I. Taylor in 1956, the proceeding, I think it was proceeding Royal Society London. So, he pointed out that current can act as a breakwater. So, it can always retard the, if there is a current, it can retard the direction of the wave propagation, and it can nullify the impact of the waves. This is one of the very interesting observation which was made by G.I. Taylor. Now, in the same way, there are currents which we can think of. There are situations where the wave is propagating in this direction. This is the direction of wave propagation, whereas the current propagates along this way. This is the speed of propagation. The current may be moving. This is the direction of current, and this is the direction of the wave. Wave propagation direction. So, this is the direction of current. This sometimes we call this as. Then this is called Z type current. There is another way that wave is propagating like this. There is a current which is a Z type current, but it is only propagating over along this strip. There is a current just in a particular strip. There is wave, and this is the direction of the wave propagation. This is the direction of current. This is the wave propagate, and in such situation, in this situation, that is called, we call it sometimes top hat current, and in this situation, there are three things occurs. One is a wave scattering, wave trapping, and no wave situation. That means, when I say no wave situation, that means there is no wave which propagate in this region. There is a situation when, because of the current, the waves will be trapped, and another time you will have a wave which will propagate to the other side, because there is a scattering, and in case of a trapping, waves will be trapped and there will not be any wave which will propagate to the other side. And another situation is that when there is not at all any wave, neither trapping nor scattering will take place, and these are very interesting phenomena. and basically for oceanographers this wave current interaction, in fact one of the major area of today's waterway mechanics is wave current interaction. And it is very interesting area when it comes to oceanography, because you have particularly navigation, marine navigation, and also understanding various aspects of the ocean circulation and modeling, but particularly when people today we go for ocean wave modeling for various reasons. One of the major emphasis is given on wave current interaction, and again I have talked about today I have talked about we have uniform current, one dimensional current, uniform current, but always you can have a current which is, suppose I consider a 2D domain, two dimensional current. In that case, like I say omega minus ku k tan hyperbolic h, and this omega minus ku, then what happen in case of a in case of a 2D current, I may have the components u1 ut 0. Suppose I consider the 3D fluid domain, 3-dimensional fluid domain. In case of a 3-dimensional fluid domain, I may have a current which propagate both in the x and y direction, and in that case my equation of free surface condition will be modified as del by del t plus u1 del by del x plus u2 del by del y square phi plus g del square phi by del t square, okay, g del phi by del y is equal to 0 for the same Laplace equation, where this Laplace equation is a 3-dimensional Laplace equation, and my free surface boundary condition can be of this nature. Whereas my bottom condition remain, if I have a uniform bed, my bottom condition remain as phi by is 0 and y is equal to minus h, and this becomes the linearized free surface condition and y is equal to 0. This is the free surface boundary condition. So, this is the way modified, and accordingly the dispersion relation also will change. In fact, I only talked about what happened in a particular case in case of shallow water. It can also be thought about in case of deep water or in case of intermediate water depth. So, these are some of the details which can be found in various textbooks, but this is just a brief introduction to wave interaction. Even if there will be interaction of linear and non-linear interaction of current, like I am concentrating here today on linear interaction. Similarly, we have in the last linear interaction we may have non-linear interaction. Because all these things, like again I have talked about interaction of, we have talked about surface and interfacial waves. In one of the last lecture I talked about surface and interfacial waves. In fact, there can be a wave-wave interaction, that means interaction of the internal wave with the surface wave. Surface and again there can be linear interaction, there can be non-linear interaction. Today's, as far as the science is concerned, major application associated with the wave propagation problems, where the realistic physical problems are handled, is based on the linear theory, linear interaction, or linearized theory of photo waves. But I say the linearized theory of photo waves. In the next class, I will tell you some of the two phenomena, how the concept of reflection and scattering comes due to abrupt change, reflection or scattering of waves due to abrupt change in water depth, reflection or scattering of waves due to change in geometry. This I will come in the next class. I will talk about this, and that again I will be emphasizing on linear interaction. So, this linear interaction, in fact, many problems of coastal engineering or offshore engineering today are handled by the linear, based on the linearized theory of float waves. I will not go to the details about wave loads and offshore structure here, because that is a different course altogether, or anything detail about coastal engineering, coastal hydrodynamics, but here as a basic emphasis I will just say that how the various how the wave propagation problems changes, or how the wave transformation takes place in various cases in brief, because the details we can discuss in other courses like offshore engineering or wave load and offshore structure, free surface hydrodynamics, or in courses like coastal hydrodynamics, ship hydrodynamics. But this course gives a very brief idea about what is happening in several cases when the wave propagate. So, with this background today I will stop here. Thank you very much.